Okay, welcome back. Now, so far we've talked about different kinds of models that can be used to simulate something real. Something that is too complicated to wrap our minds around, like a whole steam engine that can maybe be simulated or modeled using something like a simple model train or something like that. Or we could simulate the energy budget of the atmosphere using a conceptual model. Now I want to move on to the type of models that we're going to be using to understand the climate system, and those are going to be numerical models. But first I want to talk about numerical models in general. Numerical models use equations that describe the physics, the actual physics of the system, in order to simulate the behavior of the system. We're actually going to be making this completely virtually. It's not going to be real. It's going to be done. This is going to be a model in the sense of it's going to be a computer program that is simulating how something works. But it's going to be using equations that describe the actual physical laws about how something works. And probably it's best if we just do this by looking at some examples here. For example, NASA might want to have a numerical model that simulates the flight of a rocket. So like I actually swiped this slide from some NASA website here, and they had equations that are describing the physics of the ballistic trajectory of the rocket. And as the rocket goes through its path, there are different forces at work and so on. And at any given time, we can figure out the position and the speed and the forces that are working on the rocket at that time. And as long as we know those actual equations of the physics to determine everything that's acting on the rocket at that given time, we can simulate where that rocket is and what forces are acting on it. Video games are often good examples of numerical models as well. Here's a car racing video game. I don't know what game that is, but it doesn't really matter. To make the game work and to be fun to play and so on, the game is using models of real race cars. If this game worked where the cars in no way had anything to do with the real physics of how a car works, it wouldn't be any fun. If these cars could go as fast as they want, turn on a dime, never have to stop for gas and so on, it wouldn't, and could pass through solids and all that kind of stuff, it wouldn't be a fun game, right? What makes the game work is it has realistic behavior of the car. The real behavior, the real physical equations about things like how the car accelerates, or how it consumes fuel, or how much traction its tires have on the track and so on, it's what makes the game a good thing. It is a model of a car. It's not a real car. There's no real car inside of your PlayStation or whatever. It is a model of a car. It's equations that describe the real physics of how a car really works. And we simulate then how the car is acting. And they can be simple little models, or they could be very complex models. I mean, some video games probably even take into account things like the aerodynamic drag that is acting on different cars. If you picked to drive this car versus that car, how much aerodynamic drag there was, and so on. All that stuff is simulated in the model. So any kind of system can be numerically modeled, in which if we know the real governing equations that describe how the thing works. You should be able to write a real computer program that can simulate the real behavior of the system in question. If you know the physics of how a rocket flies, it shouldn't be the end of the world to write a computer program that simulates the rocket. Or if you know the real physics of how a car works and what determines how much traction its tires have and all that kind of good stuff. This computer program that can simulate the real behavior of the system in question, that's what we're talking about when we say a numerical model. A numerical model is a computer program that is using the real physics, the equations that describe the real physics anyway, to determine what the behavior of the system is going to be. Well, we want to be able to make a model that's going to be able to describe how the atmosphere is changing. And in order to do that, we need to know the physics of the atmosphere. Now, as it happens, that's something we definitely do know, and do know quite well. In fact, the behavior of the atmosphere is actually really surprisingly well described by a set of 7 equations. 7 basic physical equations that are called the 7 primitive equations. Now I'm going to let you in on a little secret. If you stick around for ATS 113 in a future semester, in the teacher's edition of ATS 113's textbook, it talks about the fact that behind the scenes, what's really going on in ATS 113 is you're learning about the 7 primitive equations. we're not showing any equations really. Well, that's not true, but mostly we don't show any real equations in ATS 113. But the materials that you're learning are really what's behind the 7 primitive equations. A theme in ATS 113 is how to model the weather. Well, the same thing is true of climate. We have a system of 7 equations that describe the climate, and they're called the 7 primitive equations. I'm not really sure what the word primitive means in this context, but we have these 7 primitive equations. Now, I'm not going to show you even one equation here, but I am going to tell you what the equations are. Now, 2 of the equations work together, and they are equations that describe forces and winds. How does this volume of air end up moving over there? Okay. And taken together, this is actually what we call Newton's second law. If you took like high school physics or something like that, you saw this is F equals ma, about how objects move when forces are acting on them. Now, the forces acting in the atmosphere are a giant mess. There's all kinds of forces doing different things, and the math is complicated, but it's actually just 2 equations that have to be solved here. There's also another equation, the third of the 7 primitive equations, that relates the pressure of air to the temperature and the density of air. Actually, if you stick around for ATS 113, you're going to learn quite a bit about that particular equation. It's one of the few equations we actually look at, and it is called the ideal gas law. Again, if you're like a survivor of, say, high school chemistry, you probably actually saw the ideal gas law in that class. But we're not worried about that, what the equation looks like or something. I want you just to understand that that's another equation that describes the physics of how the atmosphere works. Another one is about spin. There's a property of the atmosphere called vorticity that's about spin. You probably have noticed that a lot of weather features are about spin in the atmosphere. Tornadoes, hurricanes, cyclones, dust devils, things like that. There's actually an equation that talks about how, it's called the vorticity equation, and the vorticity equation explains a lot about how like storm systems in the atmosphere work. A 5th primitive equation is all about all the different ways that temperature can change. Here's a volume of air. How can its temperature change? We could have it warming by absorbing radiation. We could have it warming by conduction with a surface below. It turns out there's a whole laundry list of ways in which you could change the temperature of a volume of air. And it is an application of what physicists call the first law of thermodynamics. Again, it's a mess. It's got horrible things in it like differential equations and integrals and things like that. It's not something to enter into lightly, but it's just an equation. Okay? Students in college level courses learn the first law of thermodynamics and how to apply it to, say, the atmosphere. A 6th primitive equation that describes how the atmosphere works is all about vertical motions of the Earth's atmosphere. What makes an volume of air decide to rise or sink? This is an equation known as the continuity equation. It describes like what happens if you bring air together at the surface and there's no place for the air to go but up. It describes a lot of features about how like air comes together and spreads out and rises and sinks in the Earth's atmosphere. Again, you don't want to look at it. It's got things like partial differential equations in it, but it's just an equation. People studying at the college level learn how to solve equations like that. And the 7th one is about water. It's about all the transitions that can happen to water in the Earth's atmosphere, like changing from solids to liquids to gases as you have evaporation and condensation and all the processes, and what happens to water when it falls out of the Earth's atmosphere and runs into streams, and the whole hydrologic cycle. It actually only takes one equation, a big equation, but just one equation to describe that. What we end up here is a system. I just listed those 7 equations again. We have a system of 7 equations. That does not sound like the world's worst thing, to have 7 equations. But actually, all those equations are terrible. With the exception of the one that we call the ideal gas law, all the rest of them involve partial differential equations and integrals and double integrals, and they're a mess. All of these equations are something that people learn how to do, but are fairly horrible. That's okay. Computers don't care. Computers love to solve complicated problems, right? Well, I mean, a computer doesn't. Computer programs. That's what computer programs do. They solve complicated problems that you and I don't want to do. Computers don't care. All of these equations take a lot of fancy math to solve. Where you are in your education, I don't know, but at different points in your education, you learned more math or less math, and you learned that there's techniques to solve a lot of different kinds of problems. And some of those techniques were really easy, and some of them were a giant mess. But here's the deal. Computers don't care. Computers are darn good at solving equations. That's what we are able to program. That's what programs are, is they're ways of solving equations so that we can know something about the real world. All of these 7 equations that we're looking at so far actually only apply at a given point. Both either like on a map, like horizontally at this location, and frankly at any given height above the ground. If you want to know about the weather at this location right here, you can apply these 7 equations. But to know anything about the location at some other point, you got to apply the equations there too. And if you want to know about the weather halfway in between those 2 places, you got to apply the equations there too. Or if you want to know it at this level, and this level, and this level of the atmosphere, you got to apply all these 7 equations at all those places. Computers might have a problem with that. See, my computer got a lot less happy. I mean, it kind of depends how many points we're talking about here. But I'm going to give you a hint in advance. When a computer model is going to be making forecasts of, say, the weather, for like what's going to happen tomorrow in the weather, there are literally millions of points that they are computing the temperature, the pressure, the winds, and so on, using the 7 primitive equations. That's a lot. That's a lot of time. If those 7 equations are terrible and hard to solve, yeah, the computer's not going to care all that much about doing it one time, but doing it millions of times for all those locations and all those heights in the Earth's atmosphere, that's potentially problematic. Okay? It gets worse. All of these equations only solve for the temperature, the pressure, and the winds, and the moisture, and so on in the Earth's atmosphere at one time. They solve for those properties of the atmosphere, temperature, and pressure, and so on, for one time a few seconds into the future. That little gap of a few seconds is called a time step. We take the current data, what the weather is doing now, and we apply the 7 primitive equations, and we get a forecast of what the temperature and the pressure, the winds will be one time step into the future. And a time step, it varies from one model to another, but it's on the order of a few seconds. So if you go to all this work and apply all these equations and so on, you only get a forecast for like maybe 15 seconds from now. Well, what do you suppose you do? What you actually do is you take that data for 15 seconds from now and you apply the equations again, and now you have a forecast for 30 seconds from now. And then you apply the equations again and you get another time step into the future and you have a forecast for 45 seconds from now. And you just keep doing that thousands and thousands of times. You know, you might have to do it, 10,000 times to get a forecast for 24 hours from now. Oh, wait a minute. If you have to apply all those equations, I think computers are going to have a problem with that. My computer now here is very, very unhappy. I mean, if I have to apply all of these terrible, terrible equations at every location on the Earth, is wherever I choose I want to have a forecast, I've got to have those equations there to make my model work, and I have to do it at every height that I want to know what the pressure and temperature and the winds and so on are, and I need to do this hooray, I just applied all those 7 equations like a million times for all those million points on the surface of the Earth I needed to forecast. Congratulations, you now have a forecast for 15 seconds from now. Now you got to do all that again to get a forecast for 30 seconds from now, or again for 45 seconds from now. You might have to do it thousands of times to get a forecast of what tomorrow's weather is going to be like. Your computer is not going to be happy about that. It's going to be too big of a problem for like your laptop or something like that. Now it turns out actually that's only so true. If you only need like regional forecasts for the weather, if you only need you're just trying to make forecasts of like over the continental United States, and you don't need that many you don't need to have so many points in your forecast, and you are only forecasting for maybe 24 hours from now, actually a well-configured PC can do this these days. It used to be that this required computers that were well and above the technology that you could just go down to Best Buy and buy. Even 10 years ago, 15 years ago, this would have required like the kinds of computers that are maintained by professionals and are cooled in a cooled room, and are supercomputers, to use a better word. Today, a big PC, especially a PC not running Windows or Macintosh, but like a Linux computer or something like that, can do this. Atmospheric science majors sometimes will run a model on a big PC that we'll have set aside for them. And it's a big job, and it can usually make a 24-hour forecast in maybe 5 or 6 hours of the computer working. It's a lot of math, okay? But that's only like a 24-hour forecast. How are we going to make models that can tell us something about the climate in the future, like what the climate is going to be doing 100 years from now? That is the kind of thing that we're going to be talking about in the rest of this lecture and actually the other lectures in this module. But before we do that, let's do a little bit of questions to kind of review what we just talked about here. Question number 4. Engineers build models of experimental aircraft and they test them in wind tunnels to estimate their aerodynamic properties like drag and lift. True or false? This is an example of a numerical model. Alright, think about that for a minute. Is that a numerical model? When they're, working with it in the wind tunnel and trying to measure its properties like that? Alright, make a choice from one of the 2 options below and get some feedback before we move on to question 5.